children, my name is Shishmita. In our last part, we read about the electronic theory of compound formation. However, there are many questions unanswered after completion of this theory, like what is the shape of the molecule? Why are there so many differences in bond angle with the standard? Today, we will read VSPR theory, valence shell electron pair repulsion, which gives us all the answers. Before starting, let us revise the previous one. Ions are positively or negatively charged particles formed by the loss or gain of electrons respectively. The force between any two atoms or a group of atoms that results in the formation of stable entity is called a chemical bond. The outermost shell of an atom is called valence shell, and electrons in this shell are called valence electrons. The gases belonging to the O group are called noble gases because they are reluctant to combine with other atoms. Except helium, all other noble gases have an octet of electron configuration in their valence shells. Learning outcomes. At the end of this session, you will be able to understand about importance of VSEPR theory, statement of VSEPR theory, limitation of VSEPR theory. Keywords: valence shell, repulsion, electron pair, bond angle. Before starting this session, let's look at the concept map. Valence shell electron pair repulsion theory. To explain the bond angles in the molecules with 3 or more than 3 atoms, with all atoms attached to a central atom through covalent bonds. A theory called the valence shell electron pair repulsion theory, VSEPRT, was proposed by Sedgwick and Powell 1940. It was further improved by Gillespie and Nylom 1957. This theory suggests the following points. VSEPR theory considers electrons in the valence shells, which are in covalent bonds and in lone pairs, as charged clouds that repel one another and stay as far apart as possible. This is the reason why molecules get specific shapes. If we know the total number of electron pairs in the valence shell as covalent bonds and lone pairs in the central atom, it will help us to predict the arrangement of those pairs around the nucleus of the central atom and from that the shape of the molecule. Lone pairs occupy more space around the central atom than bond pairs. A lone pair means an unshared electron pair or non-bonding electron pair. These are attracted to only one nucleus, whereas the bond pair is shared by two nuclei. Thus, the presence of lone pairs on the central atom causes slight distortion of the bond angles from the expected regular shape. If the angle between the lone pair and bond pair increases at the central atom due to more repulsion, the actual bond angles between atoms must be decreased. If two bond pairs are present in two covalent bonds around the nucleus of the central atom, without any lone pairs in the valence shell, they must be separated by 180 degrees to have minimum repulsion between them. Thus, the molecule would be linear. If three bond pairs are there in three covalent bonds around the nucleus of the central atom, without any lone pairs, they get separated by 120 degrees along three corners of a triangle. Therefore, the shape of the molecule is trigonal planar. Did you notice that in BeCl2 and BF3, the central atoms Be and B did not possess 8 electrons around them in the valence shell? They have only 4 and 6 electrons respectively. These molecules are known as electron deficient molecules. If there are 4 bond pairs in the valence shell of the central atom, the 4 bond pairs will orient along the 4 corners of a tetrahedron three-dimensional arrangement, and the bond angle expected is 109 degrees 28 minutes. In methane molecule CH4, bond angle HCH 109 degrees 28 minutes because of 4 electron pairs bonding around carbon. If there are 3 bond pairs and 1 lone pair, that is, an unshared electron pair, then the lone pair occupies more space around the nucleus of the central atom. The remaining 3 bond pairs come relatively closer as in the NH3 molecule. In the ammonia NH3 molecule, there are 3 bond pairs in covalent bonds, 3NH, around the nucleus of the nitrogen atom and 1 lone pair. Lone pair, bond pair repulsion is greater than bond pair. Bond pair repulsion, therefore, NH3, which is expected to be a tetrahedral with 4 electron pairs in the valence shell, and HNH is 109 degrees 28 minutes, has a bond angle in HNH is 107 degrees 48 minutes due to the more repulsion by lone pair on the bond pairs. The shape of the NH3 molecule is trigonal pyramidal with N at the apex of the pyramid. If there are 2 bond pairs and 2 lone pairs of electrons around the nucleus of the central atom in its valence shell, lone pair repulsion is greater than lone pair bond pair repulsion. Therefore, the angle between bond pairs further decreases. In a water molecule H2O, there are 4 electron pairs around the nucleus of the oxygen atom. But 2 of them are lone pairs and 2 bond pairs. Therefore, the H2O molecule gets a V shape or bent shape or angular instead of a tetrahedral shape as that of CH4 due to lone pair and lone pair bond pair repulsions. HOH is 104 degree 31 minutes. What is the bond angle in a molecule? It is the angle subtended by 2 imaginary lines that pass from the nuclei of 2 atoms, which form the covalent bonds with the central atom through the nucleus of the central atom. Valential electron pair repulsion theory VSEPRT mainly fails to explain the strength of the bonds. This is because the theory still depends on the Lewis concept of covalent bond formation. It could not say anything extra about the electronic nature of covalent bonds. You have learned today VSEPR theory was proposed by Sedgwick and Powell. VSEPRT considers electrons in the valence shell taking part in covalent bond formation and lone pairs as charge clouds that repel one another. VSEPR theory helps to predict the geometry of molecules. Lone pairs occupy more space around the central atom than bond pairs. VSEPRT mainly fails to explain the strength of the bonds. Thank you.